that's left, because this I can simplify a little bit. So plus another one that's still left over there, which is another r squared sine squared theta minus 2r cosine theta is equal to 7. Well, these combine to just give me r squared. This gives me r squared. And if I wanted to, I could factor these together and put this as 1 plus sine squared theta. What did I do? I just brought this, just gives me an r squared, and this is an r squared sine squared theta minus 2r cosine theta is equal to 7. And that's a form of just.
Sorry, Professor, can you repeat how you got the r square and then 1 plus sine square theta?
So how I got from here to here, or how I
how you got
broke this up. So this I broke up. There's 2 of them, so I broke them up. Then I noticed, if I'm doing this, I can add those together. Well, let's just put in that extra step. Throw in the extra step right here, which is I pull out an r squared. So sine squared theta plus sine squared theta plus the other r squared sine squared theta minus 2r cosine theta plus 7. This is just 1. It's my Pythagorean identity. R squared plus r squared sine squared theta minus 2r cosine theta is equal to 7. Factor out an r squared over here, 1 plus sine squared of theta minus 2r cosine of theta is equal to 7. So I'm just using the Pythagorean identity over here. Getting rid of sine squared and cosine squared. And you could pull out an r over here, but then it's, I mean, what you could do is if you pulled out an r with everything, yeah, we could, but this would only be an r out front. So another way of writing it would be r, and then you'd have your r plus r sine squared theta minus 2 cosine theta is equal to 7. What is that question? Yeah, that's fine too. It's just this doesn't simplify like some other cases might do nicely.
Professor Lee?
Approaching this is you could actually square on these things and then see what happens and kind of work it out.
Professor, leaving it at the second thing from the bottom is fine too, right?
Yeah, you had something like that. That's okay without factoring. It's still technically correct. It's just good to try and get rid of, when you can, cosine squared plus sine squared. Because if you left it like this, that's fine too. It's not going to get you to the point where you're going to be able to solve for an r or an r squared. If it did, then you'd be much easier to work with that. That's all. It's just don't do so much that you do something incorrect algebraically. I would accept a lot of different answers in that regard. Now you can see we have different, coordinate systems now. And the relations or the functions that we have in those take on different values. They look different. But they would give me the same graph if I plugged everything into Desmos, and it would go to the polar coordinates to give me the same exact graph. So here, find the single xy equation from the given parametric equation. So here's what we have. We have my x is equal to sine of 2t. And we have y is the cosine of 2t. I want to get rid of the t. Now, the way we do this when you have it sine and cosine, we're going back to the Pythagorean theorem. It doesn't matter what the argument is. If I square both of them, it gives me the same sort of thing. So I square this. So looking at that, I could say x squared is the sine squared of 2t. Same thing over here. Y squared is equal to cosine squared of 2t. I want to get rid of the t, so what do? Just add both of them together. So I have x squared plus y squared is sine squared 2t plus cosine squared 2t. But what's sine squared plus cosine squared? No matter what the argument is, it's always equal to 1. So I got rid of the t. So it's equal to x squared plus y squared is equal to 1. That's an equation of a circle. Now, in terms of where it starts and where it goes, this would actually go, 2 times around for your circle if you were to let t. I didn't specify what t was here. Sometimes you will be specifying that maybe t goes from, some 0 up to, say, in this case, pi or something like that. If I said that's what t went to, from 0 to pi, that would go around once. If it goes 0 to 2 pi, it's going to flip around twice. But it's going to actually start in different cases over here. It's going to start over here at the top. So if I specify t at 0, well, x would be 0, y would be 1. And that's where it would start, and it would just rotate around from this point. And if I go around pi units, it'll take me here. But if I went to 2 pi, it would actually do a double rotation around that thing. But parametrically, that's good because maybe these things are going to represent the velocity of something that's going around in circular motion, and something goes around faster because it's got a 2t there. But that's it. It's a way, again, using the Pythagorean identity to simplify those expressions. In this case, it's an equation for a circle. And the circle is radius 1. And take a look at number 14. So here we have these other parameters. So x is equal to 3t minus 3. And y is equal to 1 minus 5t. Okay. Now, what you can do here, in either case, what you want to do is get rid of t. You have 2 equations here. So what I might do is I might take this equation and solve it for t. I could take this equation and solve it for t as well. But let me just start with this one. I'll just add 3 and divide by 3. So if I add 3 to both sides, I get x plus 3 is 3 times t. Then I simply divide both sides by 3, and I now have t in terms of x. This now tells me that t is equal to x plus 3 over 3. So what do I do with this? I take this expression for t and replace it in my second equation. I now have y is equal to 1 minus 5. Well, what's my t over here? It's equal to x plus 3 over 3. And if I want to, I could, now I just have an equation in terms of y and x. Now I could simplify this a little bit. Y is equal to 1, and multiply that, I get a minus 5x minus 15 over 3. Okay. Simplify that a little further. It's 5x minus 15 divided by 3 is 5. So I get minus 5x over 3 minus 5. I can combine the 1 and the negative 5, and I get y is equal to minus 5/3 x. 1 minus 5 is minus 4. So it's that equation of a straight line. And you can see if you're starting at some t value and going to another t value, you can see where it starts and where it stops. That's all it is. In this case, I was able to solve for it. Here, you could use, arc sine and arc cosine and plug everything in. It gets much more complicated. It's a lot easier to use the Pythagorean theorem to simplify that. 10.2 exercise. See what it is. Okay, convert the following polar equations to Cartesian form. So number 18 looks like this. And it's in 10.2. And we have r squared is equal to 2 times the sine of theta. Okay, so what do we use for here? So what we have here is we have that r squared, because we want to go from r and theta to x and y, is x squared plus y squared. Okay, and we also have the following, that if I wanted to, that my, x is equal to r cosine theta, y is equal to r sine theta. Now for this one, that would tell me then that, my sine theta, okay, is equal to y over r. But what is r? R is the square root of that. So it gets kind of messy over here. Now another approach to this, if you don't want to go this route, is very simply, I'm going to multiply both of these times r. Both sides times r. So what do I have over here? R cubed. It's equivalent to doing this. It's algebraically, it's the same thing. So it's r cubed 2 times r sine of theta. Okay. So what happens? Well, that r sine of theta is y. And my r, remember what r is. If this is r, r is equal to the square root of x squared plus y squared. So I can plug that in over here. So I'm going to get the square root of x squared plus y squared, quantity cubed, is equal to 2. R sine theta is y. Now I could even write this, if I wanted to, as x squared plus y squared, that's to the 3/2 power, is equal to 2y. So it's a very complicated expression over here. But that's what it's equivalent to. Now if you have an r over here, it would be a lot easier. Instead of the 2 sine theta, I have 2 times r times sine theta. Then it's just x squared plus y squared is equal to 2y. That's a lot easier than the other case. But because I don't have that r, I kind of have to get that r there one way or the other, either by solving for the sine, and the r comes here, and then I multiply it, so it comes over there, it becomes an r cubed, or that sort of thing. So that's how you'd handle that one.
Professor?
Yes.
If you had to take it to the fourth, would it end up being x to the fourth plus x to the y?
If to the fourth, what do you mean? If I had an r to the fourth over here?
Like if you had an r to the third to start, and then you had to take it to the fourth, would it change it to?
Well, we would change it to this: x squared plus y squared, quantity squared, which would not be x to the fourth plus y to the fourth algebraically. What it would give me is x to the fourth plus 2, plus 2x squared y squared plus y to the fourth. Because if I square that out, I get a middle term. So if this was cubed, this would be the fourth. Just to kind of show you. Because it's the algebra. A lot of people get messed up on the algebra. That's what's going to kill you in the calculus. That's why I'm having you work lots of problems in this course. You'll start to get better at the algebra, and you'll be much more proficient at it. So then what I'd end up with is r to the fourth is equal to 2r sine of theta. Well, I could write that as r squared squared, that's r to the fourth, 2r sine of theta. R squared is x squared plus y squared, quantity squared. R sine theta is y. So if I square this, remember, x squared plus y squared is quantity squared. I don't just get x to the fourth, y to the fourth, I get a middle term. So I'm distributing that twice and that twice. I get x to the fourth plus x squared plus y squared x squared plus y to the fourth. Well, these are the same by the commutative property. So that just becomes a 2x squared y squared to the fourth. So that's what I'd have over here if you squared it out. And x to the fourth plus 2x squared y squared plus y to the fourth is 2y. So if you just had a cubed over here to start with, that's what it would change to be. That answer that question?
Yes.
Good. Okay, so that is our chapter 10. And we're looking at different coordinate systems. That's why it's analytic geometry, geometric coordinate systems, Cartesian versus polar. And learning how to switch between the two. As you go further in your mathematics, that'll be important because certain phenomena have a natural coordinate system that they like to be written in. And if you find that and use that, the analysis turns out much simpler. Okay, so that was chapter 10. Then we moved on to analyzing functions and all the different properties of those functions. So if we move on to the chapter 11 practice test, let me get to that. The different types of functions, different classifications of functions, polynomials, rationals, and we also had the trigonometric and as well as the exponential logarithmic. So anything in chapter 11, practice test. Any questions there? 27 and 28. Anything else?
Number 7 and 10.
7 and 10.
I have a question. Do we have to memorize the equations for like questions 22 to
The modeling ones, no, I'm going to let you, I'm going to talk to you. You'll be able to bring in one sheet of notes, 1 8.5 by 11 sheet of notes. And I do have some of the formulas. What I'm going to put on the test, which will be at the bottom of the test, is at the very end of the book, the last 2 pages are the properties of the trig relation, properties of exponentials and logs that you will have. But if you want to take one side of an 8.5 sheet by 11 and you want to write down the basic modeling forms, you can do that. I'm not going to have you have to memorize those. And just hold that up at the beginning of the test, and then you can go from there. Anything else in chapter 11 practice test over here?
13.
13. Is that it? Anything else? Okay. So let's start with the lowest numbered one. We'll start with number 7. Fifteen, 17. So number 7 is testing for odd or evenness. So remember, a function is even if it satisfies this criteria. If I take and change the sign of the argument and it doesn't change the relation or the function stays the same, then it's even. If, however, when I multiply the argument by a negative, or change the sign of the argument of that function, and I get the original function back, however, the negative appears out front, that's odd. If it doesn't satisfy either one of those, it's neither. A function can be odd, even, or neither. So number 7, the function looks exactly like f of x is equal to x cubed plus 3x plus 5. So this is how I test. I plug a negative into the argument and see what comes out. I get my f of minus x is, I'm going to plug in a minus x cubed 3 times a minus x plus 5. So when I cube that, I'm going to get a negative x cubed minus 3x plus 5. Now, one thing we can see, this definitely does not equal my original function. So that's, without a doubt, it's not even. Now, if I try to make it look like the other one, I say, well, you know, I got 2 negatives here, so it looks a little bit like that. But the problem is, that's not negative. If I minus f of x would have to look like minus x cubed minus 3x minus 5. But my original function has a plus 5. So in this case, this will not work either. So in this case, it's a neither form. So that's neither odd nor even. It doesn't have, these are properties of symmetry. If it's even, it's symmetric with respect to the y-axis. If it's odd, it's symmetric with respect to the origin. Meaning, flip it about the x, flip it about the x and flip it about the y, and you get the same thing, or the y and then the x. And it's kind of, you'll use these things later on when you want to make certain arguments that involve symmetry that work with functions. That's why it's a tool that doesn't come up, you know, very, very often, but enough that it kind of gives you a sense. And you'll be talking at a higher level that sines and cosines and those being even and odd functions. Cosine is an even function, the sine is an odd. So you'll learn about that more beyond just this. Okay, so it's 7. And number 10. Graph the following functions using the graphing calculator or a computer app, and then describe as best you can the domain and range of each function. So here's my f of x. And it looks like the cube root of 2x plus 5. Now this is, you know, when you're dealing with a root that's not an even root, the domain and range questions are relatively easy. Because I can put any value for x and take its cube root, whether the argument of the radical symbol here is positive or negative, doesn't matter if that's a cube root. So here, domain, set of all elements x, that's that x can be any real number. And an odd root is also going to give me some strange looking stuff. So if I were to graph this by eye right now, and then I'll use Desmos, I would look at something that looks like this. So x is equal to minus 5 halves. So my graph of my function looks something like this. And x is 0 cubed with 5. So this is going to look something like this, depending upon how you scale everything. So you can also see the range for that. This is going to go from plus infinity all the way down to eventually to minus infinity. So y is any real number. And let's just plug it into Desmos. If you're not, you know, you'll have that as an option. You could also plug that into your regular calculator. Like I said, I usually prefer the Desmos app, but you know, you can use your standard TI calculator, and that should work easily enough as well. Okay, let's see if I can find, here we go, Desmos. Okay, get that set up here. I'll share my screen now. And essentially just graph my f of x is equal to, and you can, if you wanted to, you can, you know, either take it to the 3 power, or you can do a radical symbol. Let's go to the functions here. They have the basic square root, but we want something a little more complicated. So let's take a look at the miscellaneous ones. So we have it. Here it goes. that's my nth root. So it's going to be over here, it's a cube root. Oh, wrong base over here, gotta get in there. Here we go. Cube root of 2x plus 5. So zoom out, and there it is that I have my picture. It goes right between -3 and -2 as I have it over here. And that's what my function looks like. And domain can be anything, range can be anything. Now, if I wanted to, I could actually find my x and y intercept. The x-intercept over here is where the y is 0, or where the 2x plus 5 is equal to 0, and that's equal to -5 halves, or -2.5. And if you will, the y-intercept, this point over here, that's the cube root of 5, which will give me a decimal approximation of 1.71, and that's the cube root of 5. And this over here is my x-intercept. So all those features of the function we have right there. That's all it is. You analyze that function, relatively easy in that context. Okay, moving on. Take a look at number 13. There's a lot of stuff that we cover in this course, but there's a lot of stuff that you need to know to be successful in the calculus. That's why the more you see it, it'll become a little more second nature to you. So now we're looking at some rational functions. So here we have f of x is equal to x squared plus 1 over x squared minus 4x minus 12 over here. So what are we going to do? Well, let's start working on, simplifying this as best as we can. So I'm going to factor the denominator over here. I get x squared plus 1. I'm not going to factor that. That only factors into plus and minus I, and we're not going to go over the complex numbers. But this will factor into x minus 6 and x plus 2. This automatically tells me I have two excluded values. So from this, we know that x cannot equal 6 and x cannot equal a -2. Okay, so that's going to give me information about my domain right away. I'll put it over here. We'll come back to the range after we look at the graph of this. So it's x, but x can be a real number other than, can't equal positive 6, and it can't equal a -2. What are these going to be? Well, since they don't cancel out, there's no other factor over here, this also tells me that x equal to 6 and x equal to -2 are vertical asymptotes. Okay, so we're starting to piece this thing together. So let's start by going to the graph. Now you could hit the graph earlier and kind of see the picture, but it's a good idea to do your analysis first. So you make sure that you didn't hit something wrong on your computer or your calculator, so it doesn't kind of work out like you would think it should. So I go over here at -2 and I draw a vertical asymptote. I go over here at positive 6 and I draw another vertical asymptote. Okay. Now, the other thing I can look at is what happens when x gets very large for the horizontal. So I got a vertical asymptote. Now, if I wanted to, now focus on what we call a horizontal asymptote, we take care of that as well. I notice I have an x squared over x squared. I go back to the original unfactored form. When x is very large, I can ignore the constants and I can ignore the x term. So for large X, this is approximately equal to x squared over x squared, which is 1. So if I go over to here to the y value equal to 1, that is going to be my horizontal asymptote. Now, if I wanted to, I could plug in a few, numbers over here. For example, if I put in 0 for x, I get a negative 1/12. So 0 for x puts me all the way down at negative 1/12. So 0, let's put it in blue for my function, looks something like this. Now, if I want to find out, okay, does this, in any case here, does it have any, essentially x-intercepts? So now I look at this. What about x-intercepts? Here's the horizontal asymptote we just got from this little analysis. You get y equal to 1. So what about x-intercept? I found a y-intercept here. Does it have an x-intercept? Well, if I wanted to kind of look at that, what do I need to do? I need to solve this equal to 0. F of x equal to x plus 1 over x squared minus 4x minus 12 is equal to 0. Well, that doesn't give me any real numbers. I can get rid of that, and I get x squared is equal to negative 1, no real numbers. So the graph of this function will never cross, if you will, the x-axis. It's going to do something, but we don't know exactly what it's going to do. So let's see what it's going to do. Let's plug it in. We could plug in a few other points, but let's just go right to the graph. I come right to my Desmos and take a look at what it's going to look like. So f of x is equal to x squared. Well, let me get rid of this. Rid of the whole thing. Delete it. So plug that in again. X squared plus 1 divided by x squared minus 4x minus 12. Let me kind of zoom out a little bit so we can kind of see what's happening. I put in these other values that I was talked about. My x equal to 6 and my x equal to a negative 2 and my y equal to 1. Let's just kind of turn these around. Let's see, make this, graph that, but I want to change the colors and give them some dashed lines. So over here, let's see, just make this just like I have there, a red one, and do some little dots over here. The next one, oops, this wrong one over here. So come to this one. Yeah, let's just change that one. And change this one to dots as well. And then there's my other one. Let that go to green and make that dots as well. And I'll just make my other function over here. Oh, one green. Oh, well. I'll just color code it to what I have over here. So what you kind of see, it gets very close. That is negative 1/12. It never crosses the x-axis, but that value would be negative 1/12. Now here's a little tiny subtle point. The highest value it gets is at, from here, is negative 0.81, which is slightly different. It's still increasing from here. So this is 0.83, 0.083, this is 0.081 in the negative. So this point here is actually higher than the other point there. So that's going to be when we estimate the range, if you will. Now notice what happens on here. On this side, we do not cross the horizontal asymptote. But on this side, we do. So if I'm looking at this, this is the lowest point that I get to on that graph. there and there. That's going to help us with our range. So I'll just kind of, briefly write those down. So in one case I have 0.769. That's the minimum value there, and minus 0.081. That's going to help me approximate the range. What do I mean? I will never get any value between a negative 0.081 for y and a positive 0.769. So I'll never get anything out of that function in this range right here. So I have to exclude that. So y has to be greater than this and less than that. Question?
Yeah, so horizontal azimuth, so I thought it was like where it wouldn't touch the line, but how come it's touching it?
No. Horizontal asymptotes is no problem. You can touch a horizontal. It doesn't make it undefined. It's only vertical asymptotes that you can't cross.
Oh, okay. All right.
Because the vertical asymptotes make it undefined. It gives you division by 0. All this does is just makes the top equal to 1. And there's a value when, a certain value of x when the top is equal to, the y value is 1. That's okay. There are certain cases like you'll get to deal with something later on when you get to differential equations, close about damped harmonic motion, which you will go around a vertical asymptote and cross it an infinite number of times. Or horizontal asymptote, excuse me. Vertical asymptotes, that's where it's undefined, so you can't cross those. But horizontal, not a problem. That's a common confusion with a lot of students, so you're not the only one. Because everyone hears asymptotes and they hear, oh, I can't cross them. No, that's only for the verticals. So now we have our picture. I won't redraw it, but from the picture, we can take it to the next level and kind of specify the range now. So let's take a look at what would I call the range of that function. Do it over here. So the range, and this is the y coordinate. Set of all of it's y. Y again is a real number, but we have conditions. Y, and this is an approximation to the range, not exactly. So y is going to be less than or equal to a negative 0.081. So that's the highest point over here. That's over 0.83, and right over here, 0.81. So it kind of comes up very slightly. And y is greater than or equal to the other value, which is 0.7, if I'm not mistaken, 769. And that's my range. There's a range of values over here. Oh, this is negative, excuse me. I thought that was negative over here. So there's a range of values here, from minus, to this point over here. Height there of 0.769 and minus 0.081. This range of values, you'll never see it out of that function. No matter what x is, I will never get one of those because the function, as we've seen, looks something like this. So there's my vertical asymptote there. It goes up slightly, and then kind of comes over and goes down over here. And then it, kind of worked in these other, realms over here. There's reached low, and then eventually gets closer and closer. It just eventually gets settled in, and then this one settles in over here. This goes to 1, but because this one dips beneath it, it limits the range a little bit. So the functions can do some crazy things. And that's why, it's great to have a tool such as Desmos. In the old days, you needed the calculus to find that. But in the new days, now we can use technology. And you can still find it with the calculus, but it's a little bit harder to do that. Okay, so there's a lot that goes into analyzing a function. Domain, range, asymptotes, all those sorts of things as well. Here you can get your y-intercept, and that was 1/12. There are no x-intercepts for this function. So they don't have all those features. They can, well, they may or they may not. So you have to analyze it to find out. And why do we call So here we're given a graph. Let me kind of see if I can pull that up, or we could argue from the graph what's going on. And then well, let's put up what it is. It's a trait function. So we have my f of x. We're trying to fit it to this. A cosine of omega times theta minus phi plus b. So what are we looking for? We want to find A, omega, phi, and b. That's what we're looking for, to fill in those missing parameters. And it's a cosine. Remember what the cosine looks like. Cosine starts over here and kind of goes, this way. So that's what it kind of looks like. So we know that going into the problem. So let me see if I can find the textbook on that. This is on page. Okay, so let me share this and then we can kind of work it from there. Okay, let's get it a little larger so I get one more space. Okay, notice, let's figure out the amplitude. Now this is symmetric about the y-axis here. You can see there's no real shifting going on. Okay, but it goes up to a maximum of 2 and a minimum of -4. So it spans an entire range of 6. The amplitude is half of that. Okay, so I'm going from -4 up to +2. That means if A was 3, it'll take me, up 3 and then down 3, which is a range of 6. But there's a little offset that's happening here that's changing things. So what we can see right away that A is 3. Now it's shifted down 1 because if it was just 3 and B was 0, it would go +3, -3. So my B is -1. So my offset is -1. It moved it down 1 unit. Okay. Since, as I said, that looks exactly like a cosine right there, we can say for sure that phi is 0. I'll put in what I'm getting over here. I get my A, hopefully you can see that. A is 3, my phi is 0, and B is -1. Okay, the only thing now I have to worry about is the omega. Now, what is the period over here? So what we can do, it looks like if you kind of look over here, this is plus 0.66. That is 2/3. This looks like it's halfway between that. So if you looked at a period, you could say from here, I could go from, this to here. If I go from peak to peak or valley to valley, that is a period. So what do I have? I have a minus 0.333 over here in this valley and a plus 0.33. So it goes from -1/3 to +1/3. That's it goes from valley to valley or peak to peak. That is one period. So that's it. So I go, my entire period over here is equal to 1/3 plus 1/3 or 2/3. So now let's use that to find out omega. So over here, I'm going from this, valley to valley, and this is -1/3. This valley to valley is +1/3. So this entire distance there is 2/3. So what do I have? My period is 2 pi over omega. The period I just found out is 2/3 is equal to 2 pi over omega. Well, the 2's cancel out. And omega then is just equal to, just by cross multiplying, I get omega is equal to 3 times pi. So I now have this. So I now have everything that gives me my function. And what I would do is I would just double check and I'd plug it into Desmos and make sure that I didn't screw something up. If you have the time, do it. You may come back and do it if you feel like you don't have enough time. But this is the model for it. So it's 3 cosine 3 pi x or theta, I'll put it as theta, and minus 1. So let's plug that in and see, does it give us that picture we were just looking at? Okay, we share and bring up Desmos. I cleared it out. So here my f of x is equal to 3 cosine 3 pi x, I'll do x, 3 pi x, and then the minus 1 outside of that. And let's take a look at these. Let's kind of redo this. You can see it's already going from my -4 to 2, just like we had it. But let's kind of change this around a little bit. Gotta move this guy out of the way. So on the graph, let's go from -2/3. So -2/3 up to +2/3. And let's go to the step of 1/3, gives us anything. Okay. So that's the picture I'm now getting. And let's go back to what the original graph looks like, which is right over here. And you can see it's essentially the same sort of thing. So that should give me a reasonable level of confidence that what I did there is actually correct. Okay. So that's number 16, and there's a functional form. Now, a lot of times it's visual because it's, now if this had a very small, I'm not going to do that. It could have a very small phase shift that you might not notice visually, but I'm going to make it more pronounced so you'll be able to see it. So that's number 16. 17 is very similar, same sort of analysis, but now with the sine function. So we're going to use the same process. So 17, we have f of theta is equal to a times the sine of omega theta minus phi plus b. Again, we're going to find a, omega, phi, and b, the offset. And again, what does the sine look like? If I'm looking at the sine, just having a sine of just the sine, no phase shifting or anything, it's going to look something like this. So that's what my sine is going to look like. And just kind of keep going in that way. So let's take a look at the graph of that function. Now this one's a little bit more complicated. So let's go to take a look at this one. Now, what it could be, there's my, sine, this thing here, there's a couple of ways. It will not turn out to be unique. I'll talk about that. You can have several, because we know the trig functions and all the trig identities, you can have several answers for this and still be correct. First thing we'll notice, however, is the offset B has to be 0, right? Because it goes from +2 to -2. Its amplitude A has to be, or the absolute value of A has to be 2. Because it's half of that entire distance. So A is 2, B is 0. So we get that automatically just by looking at the graph. So we want to get as much as we can right away. Now, if I look at this,
what I could see is that I have appears to be a little bit of a phase shift, which is like halfway between this, meaning it's going back -1/6. But that would be if my sign had a negative out front. The other possibility is you have a phase shift that goes from 0. You could go from 0 up to, and this looks like, oh, if I make these as 6, so this is like 5 pi over 6. That's what it looks like. You have to be good with your fractions over here. So there's two ways of analyzing this. And I'll tell you what, let me show you typically what I mean on the board with that. So this is what my sine looks like. Well, what if I looked at, this is sine of x, or sine of theta or x, whatever you want to call that axis. But if I looked at the negative of the sine, the negative of the sine would look like this. And that looks like that, and then shifted back just a little bit more, a -1/6 that it comes back, a negative pi over 6, excuse me, because this pi is all down here. Or what I could do is this one, you know, it could be all the way shifted back from here. So I could take the sine and then I could shift it all the way back from here as well. So if I put the negative there versus not the negative, it's going to give me a different but equivalent representation. So that's what I might do, is I might say, okay, this is going to be the negative. That's a smaller little shifting going on over here. So that's what I'm going to do. So A over here, since I'm going to use the negative of the sine, I'm going to put the negative with A. The amplitude is still positive too, but it could be plus or minus, meaning it flips the graph of that. Okay, and this distance over here is, as I said, because I had the other one, it's like minus pi over 3, and it looks like it's half of that. Half of pi over 3 is pi over 6, and it's moving it backwards that way. Okay, so what do I have? Now, I want to find if I can, the period. So let's take a look at that and see if we can ascertain the period, meaning goes from 2 peaks or 2 valleys, and see if we can estimate that from our graph over here. So over here, let's go to 2 peaks, minus 2 pi over 3 to plus 4 pi over 3. So that's 6 pi over 3 is the total distance, right? So 6 pi over 3 is 2 pi. So this has, if you will, in this case over here, my period is 2 pi. Everyone see that? 4 plus that 2 gives me 6 pi over 3. So the distance here to there is 6 pi over 3, which is 2 pi. Okay, so that's omega is just going to be easy for us because, you know, remember the period is 2 pi over omega. So omega in this case is just going to be equal to 1. My period is 2 pi, which is 2 pi over omega. So the omega here is very simply equal to 1. I'll plug that in over here. You can't see me doing it, but I'm keeping track of it over here. But that's the analysis I did. Okay, the last thing I need to do is find this phase shift over here. Since omega is 1, that makes our life much easier. This just shifts back, if you will, a pi over 6 over here. So if I kind of set that up and plug all that in, I get my, final, if you will, answer there. Let's get a minus pi over 6.
Why is the W 1 again? I'm sorry.
Why is it 1? Okay, let me show you. Can you see why I say the period is 2 pi? Does that make sense to you? I'll leave this picture.
Period is 2 pi.
Because it's the distance between that peak and that peak on the x-axis or theta axis. So it's from minus 2 pi over 3 to plus 4 pi over 3. So the total distance is 6 pi over 3. Does that make sense?
Okay, yeah.
So that means this distance from that top to that top along this theta axis over here is 2 pi. Does that make sense?
Yeah, one revolution is 1, right? And 2 pi is 1 revolution.
Well, yeah, that's the period. You can go from peak to peak valley to valley, I could go pi over 3 to 5 pi over 3, and that would still give me 2 pi. So just easiest to go from peak to peak or valley to valley. Like this one, I went from valley to valley, and that's one complete cycle or revolution. The lowest point here to the lowest point there, that turned out to be positive 2/3. The lowest point here to the lowest point there is 2 pi. The highest point here, the highest point there is also 2 pi. Now this is by 0.667, which over here. So this distance here is 2/3 as well, peak to peak. Well, this peak to that peak is again 2/3. Okay, so I have that. I have the period. Let me then show you how I get omega. So we know that the period is 2 pi over omega. Well, from the graph, we just found out our period was 2 pi. So we got 2 pi is equal to 2 pi over omega. So omega has to be 1. Just solve that. Divide both sides by 2 pi, multiply by omega. I get omega is equal to 1. So what does this graph or this new functional form look like? And we'll plug it in. So I'm getting the following. So my f of x or theta, however we want to set this up, is minus 2, because I'm using the negative cosine, sine of the x or theta. So sine of theta minus a minus gives me a plus pi over 6. And my offset is 0, since it's going between -2 and +2. And that's what it should look like. Let's plug that in and see if that's indeed what we are anticipating out of this.
Sorry, Professor, how did you find the phase shift again?
So what I'm looking at, so I'm comparing this graph right here. And if I was to move this function upwards so that this point here just touched 0, that would be minus the sine of x. What happened? I went from this point to this point, and estimating it's about halfway between. It's not all the way to minus pi over 3, but it's halfway between 0 and pi over negative pi over 3, which is a negative pi over 6, and it's moving it in the opposite direction of the x or theta axis over here. So I just take pi over 3 divided by 2, and that's pi over 6. But it's negative since it moves it backwards. Now, I could also kind of, go from, if I wanted to, here, and I would get rid of the negative. I wouldn't have the negative in front of the sine function, and say this is 1 pi over 6, 2 pi over 6, which is pi over 3, 3, 4 pi over 6, 5 pi over 6. So I could also have, without the negative, and put the same thing as a positive 5 pi over 6. It would give me the same thing, but instead of having a negative 2 out front, I'd have a positive 2. It's not unique. That's, again, something that's indicative of all of these trig functions, because we know we have all those different sort of identities that can take and play a role. But I chose to use the negative of that. Fine, omega is 1 plus okay, let's take a look at setting this up so I can see it a little bit more nicely. So in the textbook, it looks like it's going from minus my eyes are getting so bad. So minus 2 pi to 2 pi. That's what I'm doing. Okay. Let's take this minus 2 pi. Two pi. And let's take my step to be, I'll see if I can put in pi over 6 so it can show that to you better. There we go. It does show me exactly pi over 6. And here I can go from, minus 3 to 3. So there it is. And if you go and then compare this to what we just had, I decided to put minus pi over 6. You see, this is exactly where the function goes through here. And that looks essentially like what I have happening right there. Take a look at that versus the Desmos version of that. And there it is. So those require a little extra, if you will, work to be able to do those appropriately. Okay, so I'm analyzing all the properties of these functions. And it's geometric because it's very visual. I'm looking at the period, the phase shift. I'm looking at what does a normal sine function look like. Now, I could also write it like this. I just learned this would be equivalent to 2 times the sine of theta plus, instead of pi over 6, 5 pi over 6. Because that's the other one shifted back, instead of pi over 6, 5 pi over 6. So these are equivalent. They give me the same graph. And I could show that if I wanted to. Again, just to, just so you can kind of see. These are things to kind of play around with to learn about this. Take the same thing over here. Get rid of this negative and make that a, well, oh, maybe it was 7. It shouldn't be 5 pi. I must have miscounted on something. So the purple is not going down. It's more than that. And when I counted, let me look at that graph again. And see if I had that. Let me put it over here. So let me just take this over here with the 2, and I can count it this way. This is the easy way to see. So there's the purple, and I want this to go all the way back over here. So it's pi over 2 and another. So this is 3 pi over 6. And I want this to meet to this 3 pi over 6 plus another. So it's 3 pi. So it's 8 pi over 6. That was my mistake. Plus 8 pi over 6. Didn't count correctly. 8 pi over 6. Oh, 7. There it is 7. Miscounting as I go along over here. There we go. 7 pi over 6 when I take the negative off. That's why I like to use the negative, because it's just a short little change over here. When I put that as, 0 and have to figure out, so x, I have to bring this peak to that peak. So this is a minus 4 pi. Okay, so here it is. 4 pi over 6 from here to here, and then it's equal to 3 pi over 6 from here to here. 4 and 3 gives me 7 pi over 6. And that's what it is. And it becomes the same function. So both of these are correct answers. This one uses the negative, so it was a little bit easy to see when I took the negative how to shift that. That was slightly off. This should be a 7. I just miscalculated, counted my pi over 6s. Okay, so that's all that's involved with that. So you really are getting down in the weeds and analyzing the important features of these functions. Phase shifts and periods are very important with these trig functions. So moving on to say 27. Now these are the models, if you will. The next ones are exponentials and logs. If 18 to 21, then you're looking for the logarithms, you're looking for vertical asymptotes, and for the exponentials, you're looking for horizontal asymptotes. So just so you know that. And now let's go look at some applications over here. Okay, no, we're beyond the applications. Good, that's okay. Analyze these things graphically. Now we have a polynomial function. So here we have f of x. We're just about out of time here, but I'll put it up here. 1 over 500. We should be able to get through most of this one. 3x to the 5th plus 24x to the 4th minus 6x cubed minus 4x squared minus 9x minus 6. Okay, we want to analyze this function. One of the first things we're going to be looking at is this is a fifth degree polynomial. That tells us something. We know it has a max of 5 minus 1 or 4 turning points. It's this turning going from, decreasing to increasing or increasing to decreasing, kind of like peaks and valleys, if you will. We also know that it has, because it has that, it's a maximum of 5 real zeros, which means x-intercepts. A max. This is a max. May not have all those. So we know that. It's fifth degree, so it's n behavior. We know, since it's the positive coefficient out here, the n behavior is going to look like this. It's an odd degree, so we know its domain and range are all real numbers. If it was an even, we'd have more work to do, but that's odd degree. So the domain is x is any real number. The range is also, anytime it's an odd, it's going to plus or minus infinity. So the y is any real number. So that's easy part. What we'd like to do is see if we can find those zeros, and then we'll see those turning points come up. So let's just plug this right in. So instead of using, these crazy other techniques, we can use the technology instead of using this special rule that is given in some functions that deals with the synthetic division. I don't do that. And then let's put this x to the fifth plus 24x to the fourth minus 6x cubed minus 4x squared minus 9x minus 6. Now let's change these numbers down here so they don't kind of look crazy like that anymore. I'll get rid of the pi's over here. Now, if I look at this, I have to really zoom out to start to see this behavior. You kind of see I really have to go way out here. I don't have to go too far out here. I just need to go further out in this range over here. So let me just kind of use my settings over here. I'm going to go from, say, minus 40 up to over here. I can probably go to 10 on the x, but where I really have to worry about is going up high enough over here. Down here, it's not going to go that far down, but so let me just take this as minus 100, and let's see how far I have to go up. Let me take this up to, say, 800. Even have to go up further than that. Take it up to 1,000. Looks like it's even going to have to go, further up than that. Just a little bit further. You can see where it kind of can go really crazy on you. And that's why you need technology to do this. So it looks like 15 or 1,600 would probably be good enough. So there it is. It only has a case 1 and 2 turning points, So it has a maximum of 4. It can't have 3. It has to be an even number of turning points for an odd degree polynomial. So it could either have 4 or 2. Can't have 3 because it's an odd one. But it gives me everything. Now let's see if I can figure out what some of the zeros are over here. This is where it's going to get really kind of messy over here. So I have zeros. One is at 1. Another 0, I don't know here. These look like they're kind of related to each other. So I have a 0 at 1. I'll come back to those. And it looks like over here, that's a little bit harder to get. I'm not going to make it this hard. I think it's off a little bit. X to the fifth. Oh, that's why. I didn't notice. I left something out. So that will change it slightly. I didn't notice this. That will kind of change things a little bit over here. Yeah, so it changes it quite a bit. I had a 3 over there, so I don't need that much. So I can go to 100. Yeah, it's little typos as you get along the way. We're out of time, but you can kind of see I only needed up to about, 45 or something like that. And then over here, minus 20. Okay, so that looks a little bit more manageable. Again, these look like they're in, some quadratic formula. So over here, that's another 0 here. So it's 1. We're out of time right now, so I won't go too much further. But the ones on the test will be much more manageable for you to be able to find these for these zeros if I ask you to find them. But here, what we could do is get an estimate of those zeros. So we have this one looks more like it's 0.972. These are all estimates. 0.571 minus 0.516. And we have this other one minus 8.228. So we have 1. And you see 2, 3, 4, 5. It has, in this case, 5 real zeros.
That
Oh, no,
function
sorry.
still has 2 turning points.
Yes, because it's okay. Look at the turning point. It's increasing. See, it's getting larger and larger and larger, right? Then it stops from increasing at that peak and goes down to decreasing. So it's changed its behavior. Now I'm decreasing, 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 and see what happens over here. Let me zoom in. I'm getting smaller and smaller until I hit its base. And the lowest point, kind of occurs somewhere along the line over here. So it's not, that's a 0 over here. That looks like it could be a lowest point, or it could be over here. Here's the lowest point that I get. Yeah. So it's the lowest point minus 0.022. So over here. So it has this one over here. As well as, since y is 0, that's a 0. Y is 0, that's a 0. This is not a 0. This is my lowest point over here. And that's why I'm going from decreasing. And after that, it goes to increasing. It goes from negative 0.022 to 0. So decreasing to increasing. There's my x-intercept, lowest point on the curve. So I have 1, 2, 3 zeros, if you will. It doesn't cross the x-axis ever again. And that's all it is. So if it's an odd degree, it can only have an even number of turning points, and it has to be less than the degrees. So it's either 4 or 2. In this case, that's a maximum. It can have 4 or 2. If this was a 7th degree, it could have, in this case, 6, 4, or 2. And that's all about the fundamental theorem of algebra that we got to learn that. But that's everything there. And 28 is kind of like, that one we should have started with. That's a much easier one. That's just a very simple parabola, and you can solve that analytically. So 28 should be fairly easy in comparison. Now you can put it in if you wanted to and find the